Let's look at this practice problem. To clarify, I have 5 boys: Mario, Juan, Gustavo, Calvin, and Philip. I'm going to write above them what I'm going to refer to them as. They want to go to the movies, but there's only 3 tickets left. How many different options are there for the 3 of the 5 boys to attend the movie? So just like I did with the permutation in the permutation video, let me pick one option. Let me pick M, K, P. Let's say those 3 boys go. Now another option using those same 3 is K, M, P. Are these the same? For this example, are these the same? If Mario, Calvin, and Philip go versus Kelvin, Mario, and Philip, yes, they're exactly the same. They're exactly the same. It doesn't matter the order in which I write these letters, the same 3 people are going to the theater. Order does not matter. I'm going to write that again up here. This is a really important key point. Order does not matter. This is a star. Another key point is that no repeats. So I'm not allowed to just give all 3 tickets to Mario, basically. Because order does not matter, this is a combination formula. So the combination formula is n factorial divided by r factorial times n minus r factorial. N is the total number of things, the total number of objects, so that's 5. The number that are actually going to the theater is 3. So let me plug it in. 5 factorial divided by 3 factorial, 2 factorial. You should just end up with 10 ways. There's only 10 ways to do to assign those 3 tickets to these if we were working with 5 boys. So let me go on to the next practice problem. The best basketball team in the entire world, aka the San Antonio Spurs. Yes, I am a San Antonio Spurs fan. Has a roster of 12 players. How many starting 5s, or the first 5 players on the court, can be chosen from these 12, ignoring positions? So this, obviously, there's no repeats. Once I choose one of the players, I can't choose that player again. I'm gonna just to make sure I know what the hell I'm doing. Let me call the 12 players 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are the 12 players. So let me pick 5 of them randomly. 5, 6, 2, 3, 11. Those are 5 players. Now let's say, what if I shuffle those around? 2, 3, 11, 6, 5. If I'm playing basketball, and I have these 5 players on the court 1 minute, and these 5 players on the court the next minute, are they the same? Yes. Yes. The same 5 players on the court. That means I'm going to use a combination. My formula for a combination Combination, if I have n total objects and I'm grabbing r of them, is n factorial divided by r factorial, n minus r factorial. So let me identify my variables. N is the total number of objects, 12. R is the number I'm grabbing, that's 5. So let me plug them in. 12 factorial divided by 5 factorial times 7 factorial. So let me plug that into my calculator. 12 factorial divided by 5 factorial times 7 factorial. And I get 792. Wait. Just to show you, that's what my calculator looks like. Right here. Okay. For number 3, determine if the following statement is true. There are fewer than 2.6 million 5-card hands from a deck of 52 card playing cards, but more than 635 billion 13-card hands. So I'm looking at 5-card hands from 52 cards and 13-card hands. I don't know if this is true. What? So I'm gonna do it for myself and see if they are true. If I have, I'm not repeating. Once I pick an ace of spades, I can't pick an ace of spades again. Okay, that's how I know that's true. Let me see if order matters in this case. So I'm going to come up with 5 cards and rearrange them. So let's say I have 5 of hearts, 6 of hearts, 7 of, I don't know, spades, jack of diamonds, and ace of clubs. Those are my 5 cards that I have in my hand. Let me rearrange them. 7 of spades, jack of diamonds, ace of clubs, 6 of hearts, and 5 of hearts. Is this the same in this example? So if I have these cards in my hand one shuffle and these cards in my hand the next shuffle, yes, they're the same. So I don't want to count them as 2 different things. That means I'm going to use a combination. Just as a refresher, the combination formula, C of n comma r, is n factorial divided by r factorial times n minus r factorial. My n, the total things I'm grabbing from, I'm going to start out with the 5-card hands, but the total things I'm grabbing from is 52. And first I'm only going to grab 5. So I'm going to show you a shortcut in your calculator. You can go to on in the calculate screen and type menu and go down to probability. And here I have all these awesome options. You can also get to factorial here. You can get the permutation formula. I'm currently using the combination formula. So I'm given the option of NCR open parentheses. The first number that goes in here is your N. So in this case, my N is 52. And my next letter that goes in there is the R. So it's 5. So let me type in 52, comma 5 and push enter. And I get that this is 2598960. So my first question is to ask, is this fewer than 2.6 million? Yes, I'm going to put a check mark there. It is fewer than 2.6 million. Not by much, but it still is. Let me do the same thing for a 13-card hand. So again, this is for the 5-card hand. Now I'm going to do it for a 13-card hand. I don't want to write down 13 cards, but it's the same example. If I have 13 cards and I rearrange some of them, it would still be the same hand. So my N, I'm still going to do the combination. C of N comma R is N factorial divided by R factorial, N minus R factorial. N, I have 52 total. Now I'm choosing 13 of them. So let me plug it. Actually, I'm going to do N CR in my calculator of 52 comma 13. Sorry, 52 comma 13. And I get a really big number. Let's see. 63501355960. Okay. And that is 635 billion. And it's more than 635 billion. So let me go back. Yes. So overall, this is true. And there's my supporting work. Let's go to these extra practice problems. Suppose that I invite 3 friends to go with me to a concert, and I have 7 friends that want to go. I write the 7 names on a piece of paper and put them in a bowl. Then I randomly choose 3 names. This is pretty much telling me, determine why I'm using the combination formula. So first I'm going to find the number of combinations and explain why I'm using combinations and not permutations. So my combination formula is C of N comma R is N factorial divided by R factorial N minus R factorial. N is the total number of people I'm choosing from, so here it's 7. My R is the number that I'm choosing, so it's 3. 7 factorial divided by 3 factorial times 4 factorial. Or you could use the combination thing in your calculator, so it'd be 7 comma 3. It should be 35 ways. So I've determined the number of combinations. Now I need to explain why it can be solved using combinations but not permutations. The main difference between combinations and permutations is whether or not order matters. So for combinations, order does not matter. So if I invite Miss Vesperis, Miss Mata, and Mr. McCreary to the theater, that's one option. But what if I write it Miss Mata, Miss Vesperis, or Mr. McCreary? Are these different? No. The same 3 people are going to the theater. Order does not matter. Because there's no rank in this problem. There's no ranking. So let's go on to number 2. Sam bought a machine to make fresh juice. He has 5 different fruits: banana, oranges, apples, pineapples, and lemons. If he only uses 2 fruits, How many different drinks can he make?